So we just finished looking at how tangent lines give us the slope of a function at single points. Well, what if we made a tangent line at every possible x value on a function and then plotted the values of those slopes at their same x values? We would basically end up with a graph of the function's derivative. So the idea of the derivative is really pretty simple. It's a function that we call f prime that gives the slope of a function rather than its y value. We can mathematically calculate a function definition for the derivative of any other function by using the limit expression, but we can also do this graphically, and I think that's a really good connection to make here. We basically want to get each of these little tangent lines to be tangent to the function where they are. So I've got 9 different tangent lines here at different places. Now we're starting off with a line here of y equals x. So I know that that's the case because it passes through the origin, and I have a delta x of 1 and a delta y of 1, so the slope is 1. So if I adjust the slope of that tangent line to a slope of 1, it gives me this tangent line right here, which is tangent to the graph. And no surprise, if I set all of these to 1, each of my little tangent lines, my tangent segments if you will, are going to be lined up nicely. And bear with me a second, I'll just go ahead and finish this up. And no big surprise, the slope is 1 at every x value. And so if I plot the derivative, I should get my derivative function f prime. If f is equal to x, then f prime is equal to 1 because that's the slope of the function x. And you can see that these red dots lie on that line because when I adjust the red dot to a value that gives me the slope at that point, it should be a slope of 1. All right, let's try another function here. I'll reset this. And let's pull up 2 times sine of x. Okay, so you should be familiar with the sine function more or less graphically here. I've multiplied it by 2 just to make it a little bit taller. And so we're going to go ahead and adjust these so that we get all of these little segments tangent at their points. So here we can see that we want a negative slope because the green function sine of x, 2 sine of x, has a negative rate of change at that point. So I'm just going to drag it down until I get, that looks pretty good, something that looks tangent. Once again here we have a negative slope, looks like a bigger negative slope, so I'm going to go ahead and do something like that. Another negative slope, maybe not quite as negative, maybe somewhere around there. Positive slope in this case, maybe something like that. Positive slope. Smaller positive slope. This is a negative slope again at this point, so I'm going to go negative here. Bigger negative slope, and not quite as big of a negative slope. And so now if I click this, I get the derivative graph, and it goes through the points pretty well, so I did a pretty decent job. And guess what? That graph is 2 cosine of x. So the derivative of f of x equals sine x is f prime equals cosine x. And really, if you think about it, that's a pretty interesting relationship. The cosine function then is going to tell us a lot about the sine function. If you want to try some other functions, go ahead and just type them into this box and then hit enter. And then when you drop the box down, your function will appear down at the bottom of the list. You can also click this button up here to reset. I want to show you one more function here while we're at it. E to the x is a very special function. It's one that you probably didn't know much about until last year, and even now you might have forgotten a little bit about what we talked about. But in any case, let's go ahead. I'm going to just drag this down a little bit. Let's go ahead and adjust at least a few of these sliders. This graph is going to go very high very quickly, so I may not be able to get to these 2 points here. But we'll go ahead and adjust these other ones here. Now, even though this looks like it's right on the x-axis, we know that it's slightly above, and it's getting a little bit bigger as we keep moving to the right. So it's actually a slight positive slope. I don't want to go quite that much, so let's say right about there. This will be a little bigger positive slope. A little bigger. It looks like the slope just keeps getting bigger, and that's what makes it curve up. This is a bigger positive slope. I think you can see already what's kind of magic about this function. The function e to the x has a derivative of e to the x. It's the only function other than f of x equals 0 whose derivative is the same as the function itself. And this is a really important concept in exponential growth. Basically says that the rate of growth is equal to how much you've got. We know that populations are modeled by exponential functions, and basically that means the more people you have, the faster the population is going to grow, and that basically makes sense. The base of e is special because its rate of growth is exactly the same as its value. Other exponential functions will differ by a coefficient, by a constant. So have fun with this and see if you can get the idea of the derivative by messing around with this particular app.